I'm Gary LaRue, Technical Editor at Microwave Journal. It's my pleasure to welcome you to today's webinar with Art Aguayo of Rogers Corporation, discussing a materials perspective on the development of 5G. Before we begin Art's presentation, let me cover a few items so you know what to expect. It will last an hour. After the formal presentation, we'll have some time for questions, which you may submit at any time. Just type your question into the Q&A panel on the right-hand side of the WebEx screen. Please address the question to all panelists, which is the default setting. After the webinar concludes, you'll receive a copy of the slides. We are also recording the webinar so you may watch it on demand and recommend it to colleagues who aren't able to watch it live. The recorded version will be available in the Events section of the Microwave Journal website within about 24 hours. Let me introduce our speaker. Aguayo is the Senior Market Development Manager of the Wireless Telecom Networks Group at Rogers. He's been with Rogers Advanced Connectivity Solutions for over 20 years and has held various positions in engineering, quality assurance, and marketing. Art has a bachelor's degree in electrical engineering from the Monterrey Institute of Technology in Mexico, a master's of science with a focus on electromagnetics from Arizona State University. Art, on the screen, over to you.
Thank you, Gary. Good morning, good evening, everybody, for joining us on this presentation. As we titled, a materials perspective on the advances in technology for the road to 5G. So here we will cover, we'll be covering the areas of and data here on a little bit of a brief summary of 5G, or at least what we tend to have seen as to this very broad and very interesting subject. We'll talk on the material choices from the high-frequency printed circuit board materials, the various resin systems that are being mainly used in some of the newer ones coming out. We'll talk also in general on the detailed characterization of these materials, especially since some of these applications will require use and frequencies that very high 77 gigahertz millimeter wave frequencies. We'll also talk about PCB manufacturing, something that very important. It is something that we're seeing that these kinds of applications, this kind of market will require very complex circuits and a better understanding by the designers as to what can or can't be done would really help in essence for the whole process of this design for manufacturability, DFM. And of course, as we said, it will leave plenty of time for a Q&A session at that point. To start first, let me just give you two brief slides on Rogers Corporation, in case some of the folks here are not as familiar with Rogers. But Rogers has been producing high-frequency circuit materials, the Advanced Connectivity Solutions group, over 60 years. So high-frequency circuit materials that started out with PTFE resin-based materials since 60 years ago. We have a very broad portfolio of products, various kinds of resins for various kinds of applications, as well as resin systems that are for non-high frequency use, but some of them might be more for thermal management as well. Also, we have a very, very differentiated product line, some very, very high performing materials, some other materials that may be more customer, more cost effective, more cost focused for higher applications that are moving up in frequency band that traditionally we're using more of materials that are more traditionally like the FR4s. Overall reliability of the materials is very important to Rogers. We like to work a lot with our customer base, our OEM designers, as well as the fabricator to be able to help design products that will be successful in the market with those strong relationships. And overall, a true global footprint. Rogers does manufacture many of these materials in various locations around the world. We're headquartered in the United States. Our main manufacturing facility is in Arizona, but we also manufacture in Belgium and as well in China many of our high-frequency materials. So these materials are used. Traditionally, the original high-frequency market was the aerospace and defense. High reliability market, that is still a very important market to Rogers, very strong opportunities there and still going through many, many changes. communication infrastructure, which is one of the main reasons we're talking about here, just keeps changing, keeps evolving from 2G, 3G, 4G, and now we're obviously talking about 5G. Materials used in antennas, power amplifiers, microwave radios for many years. Also, Rogers has been producing materials that get used in satellite communications, particularly satellite television, LMBs, low noise block down converters, and then the emerging markets are the automotive, medical security, but many automotive radar sensors using Rogers materials at these frequencies already, high enough frequencies of 27 and 77 gigahertz already for some time now. We have the mobile infrastructure, mobile internet devices, as well as high-speed digital, which is an area that as data rates are increasing, we're seeing now that RF is actually being part of the equation for high-speed digital, folks. Enough of the background. Let's get started with the material itself. Let's talk a little bit about a brief summary of 5G and where this tends to go. So what we see, from where we stand, when you look at the overall value chain, the supply chain of equipment into wireless infrastructure, well, Rogers sits at the bottom of that chain, right? We are the high frequency circuit board substrate material that a lot of the technology then is placed upon and then built upon to be able to use our communication systems. So from where we stand, we're following really what's happening overall in the data demand. It's one of those things that, as we always say, chicken or the egg, is the demand driving the infrastructure development, or is infrastructure allowing us to go into demand with higher data rates and more data. But what is something that we have seen over the many years, and the data presented by Cisco on a yearly basis updated, is how much mobile data is growing. It has been, in the past, it's grown over 4,000x in the past 10 years as we've gone from one technology to another. It is projected to still grow by a factor of 8 through 2020. I think what is an important factor here to look at is when one compares data, mobile data, very heavily driven by video, is the fact that you can look at the 2020 data, and when you see the growth of 2020 compared to 2019, the growth itself, it's 2 to 3 times the size of all the data in 2015. So it amazes people to see how much data will be going through mobile networks in the future. And the more we see of what's happening, I think there's no doubt that is truly what we will continue to see. Global devices continue to grow, connected to cellular networks. This is what this data presented here. Obviously, there's many other devices that we've been hearing about that will be connected, maybe more hardwired on the IoT, but overall, everything is going to be connected. Smartphones, phablets, basically making up over 50% of all devices by 2020. So that is a big driver. So we will have the technology, the drive for the data, and the technology at our means to do that. Sense of 5G, how is that different? 5G versus where we are today with the 4G and the LTE Advanced. Well, the ITU's vision of what they're defining as IMT 2020, the official technical name of 5G, we're seeing that you look at various of these parameters of what they can see is important to look upon as the parameters to define the difference of one product versus the other. So it's an evolution, and going forward, enhanced mobile broadband, we will see that will benefit from improved data rates, spectrum efficiencies, and overall mobility. So those are sort of the some of the parameters that are important to them. While the ultra reliability communications will seek for low latency and peak data rate improvements, and then when we massive machine type communications, which is sort of the IoT, what we're hearing about, obviously the improved connection densities and network energy efficiencies are important of this. So not any, the overall spectrum of what parameters are important don't apply to every single one of these applications. As we see the self-driving vehicles, ultra reliable, and latency is important. Is very, very important to them. That is what we tend to see is a focus of certain business cases, and then picking within those business cases which ones of these parameters of INT 2020 or 5G is truly important. And we're starting to see some branching out of certain groups, focusing on some early business cases for that. In us, is overall what we're finding is that there's a breakout on the frequency use for many of these applications. Broadband availability, spectrum availability for all this data to go through is important, and we know that the lower frequencies is very saturated already. Many uses, so sub-6 gigahertz still is an important area because that is what it's more of the evolution off of 4G. The LTE advanced systems kind of more work in that area. Actually going into the IMT 2020, many of these really will most likely be operating in the 20 to 40 gigahertz and plus 60 gigahertz range. We're tending to see 28 being some of the early frequency bands because it's available quite in many places around the world. There have been talks about other frequencies like 15 gigahertz, but that's more of a more Europe-centric availability, not as much in some other parts of the world. But 28 is one that we really are seeing, and of course 77, some of the more open, very large areas of spectrum available, but of course more complex and more expensive. From a technology perspective, the concept of MIMO antennas has already been deployed with LTE, but now we're talking massive MIMO. And when you do and talk to people about the differences between massive MIMO and MIMO, we tend to hear that when your arrays ends up being where you have 64 elements in your array, they're kind of saying we'll call that massive MIMO at that point, but many of the functionality is common in the sense of beams. You might have beam steering as well, and form shaping, and then to do this, you will need to work with very complex multi-layer structures to be able to have this level of control. So those are the things that we've been seeing in a sense from general overall workshops, seminars, presentations. We saw at the CTIA or earlier this month in Las Vegas. It's a lot of the talk in this 5G, and that's really something that is no longer really a matter of really truly will it happen, but it's just is more of a talk of when exactly and what would be the business cases that will first drive this growth. So now start talking a little bit about, as a designer, looking at these the applications or looking at frequency bands, what material choices are available to designers. We'll go ahead and get that portion started. So we really start looking at the two broader frequency bands or frequency separators. Sub-6 gigahertz is what we're seeing, at least more the early phase of what a 5G or what sometimes gets blurred as the LTE advanced or LTE plus, and then before going to full INT 2020. In these frequency bands, we're seeing that the sensitivity to decay variation is it's important to control thickness variation to be able to have very repeatable circuits. High thermal conductivity, maybe even higher dielectric constant values to reduce the sizes of the circuit boards is something that we're seeing happening as well. And then, of course, that the materials that are being used be able to be processed in a way that one can do multi-layer board designs. In the higher frequency bands, millimeter wave, we tend to see the need for thinner dielectrics, smooth copper foils in order to reduce losses at the higher frequency bands. Becomes more and more important. Also, the low dielectric constant values as well is an important factor. And mechanical properties, we're starting to see more and more device integration, surface mount on many of these devices. So the processing and mechanical properties that would be more commonly found in maybe some of the digital boards where they have a lot of this integration is also something that is important for the designs. So in looking at the materials themselves, divided the grouping slightly different from how we tend to see materials in the past, mainly because of the frequency band differences. So here we're talking about the low dielectric constant materials first. Typically, some materials that range maybe around 2.2. Some materials are around 2.17. Some may be around 2.3, but typically they're around the 2.2 value in dielectric constant. The mid dielectric constant, maybe for terminology, DK, dielectric constant, relative permittivity. I'm using these interchangeably with each other, but the mid dielectric constant values are those materials that tend to be in the 3 to 4 value, and then the high dielectric constant materials are, at this point that we're using for presentation will be those that are in 6.15. There are materials with higher dielectric constant, but usually what we're seeing for these frequency bands, 6.15 is where we tend to see what of more interest here. From a PTFE low dielectric constant, these are the materials that have been around the longest. Frequency bands can go pretty high because they have very low loss. These are materials that are typically PTFE, Teflon, trademark from DuPont, but PTFE resin with glass. It is either in dispersed microfiber or it might be a woven glass layers. Typically, these materials have a content of PTFE close to about 90%, so they're almost quite a bit of almost all resin with a little bit of glass. And then the dielectric constants, like I said, 2.17 to 2.2. Electrically, the materials offer the lowest loss solution. Loss tensions 0009, 001, maybe even slightly lower than 0009. You also will see that these materials have much tighter dielectric constant tolerance. Although I will say this, that when one is looking at repeatability of the circuit, we find that thickness control is as important as the dielectric constant control. So that is something that always take into consideration when looking for repeatability in materials, is also look at the thickness tolerance and the impact on the impedance variation versus dielectric constant. Because they are very high in resin content, they tend to have higher z-axis expansion values, and this could be a concern depending on how thick a multilayer might need to be for the application. So that is something that we always tell people that when evaluating these in a multilayer structure, that care be done in doing the evaluations for plated through-hole reliability. Also, PTFE itself can go through a significant change in dielectric constant versus temperature. So sometimes in environments that have a lot of fluctuation in temperature, these materials by themselves may not be the ideal solution, but they do, like we said, offer very, very low loss. And it can also be because of the high PTFE content that tend to be more higher priced materials out of the products that are here in this presentation. When we PTFE mid dielectric constant category, these materials that are using typically PTFE and some kind of ceramic particles. Some of them may have woven glass. Some of them may just be the PTFE and ceramic. And obviously the glass and the and the ceramic are used in essence for mechanical support. The advantage of the resin of the ceramic is that it acts as a stabilizes some of the variation on the PTFE when it comes to mechanical and electrical properties against temperature. So these materials have excellent plated through-hole reliability. That is one of the claims to fame with a lot of these materials, and the mid-dielectric constant is that they are being used in complex multi-layer boards and have very high reliability. That's how they were early on the first generations of these products that were used in more of the high reliability space defense programs. So now we're trying to work on material versions of these that can also adapt more to a commercial market space. The one thing that happens here is now you go up a little bit in the loss of the materials. The loss tangent starts going up a little bit, and also the dielectric constant value does go up and move away from just being a pure PTFE resin, which PTFE itself is around 2.1 dielectric constant. The next thing is then the thermoset. So up to now, the PTFE materials, what we would call thermoplastics materials, that when you heat up, they go through a melt stage, and usually these melt temperatures are in excess of 300, 325 degrees Celsius. The thermosets, these are materials that during the lamination process by the laminator, they change in basically in the nature of the chemistry, and therefore now you have a rigid material. Mechanically speaking, these materials tend to have mechanical properties very similar to traditional FR4 epoxy glass kind of circuit boards. They don't have the PTFE, as we said. It's a different kind of resin system, low loss, not as low as PTFE. And they also use ceramic filler, and typically these materials are coated on a woven glass matrix to give the individual layers that get stacked up to give the various different thicknesses that are needed. The advantage of these ones is that they tend to be the best materials in the market. The thermosets, they have the lower cost and lower conversion costs for circuit boards and the FR4 process world, particularly when you're talking in a multi-layer structure. So you do a balance of performance versus cost of these materials compared to the PTFE base that would have a higher performance, lower loss materials, but have a higher cost of adoption. So that is the way that these materials tend to separate. You have in the area of high dielectric constant, you do have some of the thermoset materials as well. There are some PTFE also in this frequency band, but we're seeing now the introduction of newer materials in the market that have a high dielectric constant thermoset, so that to be able to benefit from the advantages of the mid-decay thermoset material, what's happening in that market. The same thing is happening now in the higher dielectric constant with some of the newer materials. The dielectric constant of these materials tend to have a dielectric constant close to that of LTCC, low temperature coefficient ceramics. So we're beginning to see adoption from LTCC away from that towards these kinds of materials. Now, the last row here is a newer resin system that really offers a very unique properties. It's really the only one that typically is available as a pure resin. It doesn't come with a ceramic filler particles or with woven glass. The advantage here is that you do have a material that's very thin, low loss, dielectric, that can be used in some multi-layers. It's a thermoplastic, so usually what's called sequential lamination, where you may have to have buried vias, and your process would not accommodate well here. But in single-stage, multi-layer lamination process, this kind of resin system is good. 25, 50, 100 micron, 1 to 4 mils in thickness is common for these materials. And they're starting to see, definite more from just the early on interest on more R&D projects towards actual applications that are using these materials to make very thin interconnect layers. Specifically, is quite of interest for high frequency, flexible interconnect RF connections here. So in general, I would say the important thing is that in selecting the material, one has to look at the overall function cost that one is trying to reach, and then see and working with these with which options is best suited. There's no one that I would say, oh, this one material will work in all cases, because it's a balance of what the cost targets, functionality, design goals are designers trying to achieve, as well as the fabrication and for manufacturability and purpose of what one is trying to achieve. Another thing to consider, and we'll go into a little bit more detail in the next other stages, is that what we found is that when selecting the materials, you also have to talk about it's not just a selection of the pure dielectric. It is important to which copper types one's using. It is, as we go higher in frequency, conductor losses, part of the overall equation of the insertion loss of a material, dielectric, copper, and then of course there's always radiation losses in the case of microstrip. But the important factor here is when one is looking at copper is looking at the impact that smooth copper has versus rougher copper. Traditionally, many of these materials come with options of rolled copper or electrodeposited copper. In general, rolled copper has a smoother surface that is the interface between the copper and the dielectric. Smoother means then with conductor losses, so that's an advantage. The higher the frequency or the thinner the dielectric, this is more so a factor. The added benefit we found, and here we have an example where we measured one of the Thermoset materials from Rogers, the RO4350. We were looking at the version of a low-profile electrodeposited copper that is trademarked low profile, and then the traditional electrodeposited copper that typically comes with this material. You can see, at least on the graph, the difference in the insertion loss when one measures the Microstrip 50 ohm insertion loss for this 10 mil material. You can see the benefit, the improvement in insertion loss when you're at 30, 40, 50 gigahertz, when some of these applications may be. But the added benefit we found here in doing some thermal imaging is the impact in the reduction on RF heating can be significant as frequencies go higher. In this particular case, we measured a 3.3 gigahertz circuit trace with 85 watts going through the line at 50 ohms. And you can see the difference of temperature rise of that trace to the surrounding surface and how hot it gets with the traditional copper, and then the difference in temperature versus the low pro. So you're looking at almost about a doubling in temperature rise difference here. So you go from 34 degrees Celsius in temperature rise for the regular trace versus 19 degrees Celsius temperature rise difference in the trace that is using the low pro foil. So besides besides the temperature, the losses, you also have the value of temperature. Detailed electrical characterization. So as said, here we have a graph, and you'll be able to, when you download the presentation, be able to expand this thing a little bit higher, better resolution. But what we're doing here is we're showing a series of products of Rogers that have various dielectric constants or loss tangents. And then many of these have different copper roughness types. We're kind of trying to, out of the materials that we've selected here, we've shown some of the materials with the lower dielectric constant, best coppers, smooth coppers, versus some of the products that have with the rougher copper. You can see the band in between. So working and talking with your copper, your laminate supplier would be important in having the proper choice in the balance of, not always do you go with the smoothest copper, because there's always a balance of what happens to peel strength. So depending on the application and the reliability concerns, is what is the lower insertion loss with the smooth copper important enough to maybe overcome the concerns that you may have with lower peel strength. So one of the things of the balance of loss and peel strength with the roughness of the copper. When one of the dielectric constant, the frequency of the various materials, people will usually ask us. I've have experience with these materials at this particular frequency, 10 gigahertz. I want to use it at 30, 40, 70 gigahertz. What happens to the dielectric constant? In general, the data that will be presented here, you'll find that dielectric constant over that broad frequency range does not change very much for these materials. In the case of PTFE, low dielectric constant materials, for this broad 1 to almost 100 gigahertz, you're seeing about a change of 0.05. Unless you're talking about a high-speed digital 40 gigabit systems that encompass a very broad band, this overall change probably won't matter so much, because most high-frequency applications in the RF world typically operate in a narrow band of this overall spread that we showed here. It's those digital systems that can operate for 40 gigabits from 20 to about 100 gigahertz when you're operating at a 40 gigabit system. But unless we have some digital designers here, that wouldn't be so much of a concern. And so the mid dielectric constant material, same thing. you can see the change is slightly higher as you kind of move away from the pure resin, PTFE, and some other mix-up materials. You're going from maybe 0.5 to 0.1 in overall change in dielectric constant. Again, in these applications, we'll find that at 40 gigahertz, you're staying mainly around 40 plus or minus a couple of gigahertz. So you'll see within that it's a very, very, very flat value. And look at some of the materials with Thermoset. You can see here one of the things that I want to point out is that besides the impact on the loss of rough copper is what happens to the dielectric constant change, the slope of this curve, when you're comparing a smooth copper foil with one that has a rougher copper foil. So you see the same material actually displays what we call an apparent constant difference because of the impact of roughness it has on the phase velocity of that signal, and how that translates into an effective dielectric constant. So when you're using a material and in your design software for a simulation, you have a value and you're using the same material, but now you're using a smoother copper, that actual of dielectric constant for better accuracy of model versus measurement will change because of the roughness of the copper, even though the dielectric itself does not change. So you can see that from the value of this particular material. In this case, is the R4000 material. That with the smooth copper, it is a lower value of 3.55 about at 10 gigahertz, while it's about 3.8 at a higher with the rougher copper at about 10 gigahertz for, in this case, this material itself that's being evaluated here. The loss materials, you'll see here the impact of rolled copper versus electrodeposited copper. You can see the difference that happens with this material. This is very thin dielectrics, 5 mils, versus the RO3003, which is a PTFE ceramic product from Rogers. That is, you can see the impact of rolled copper versus the ED copper difference. So you can see definitely that when using rolled copper in with these various of these materials at higher frequencies, there's a significant benefit to that. So that is important for the higher frequency bands. Looking at some of the mid-dielectric constant materials, this is from Rogers, the RO3003 and the RO4000 materials. RO3003, you can see same thing, same benefit on the products. You can see here, use this graphic to then look into what is the benefit of using a PTFE over a Thermoset on insertion loss. As we said, there would be usually a price concession when you go to higher performing materials. So this is one area where a designer would need to say, at 25 gigahertz, what is the benefit of going to 3003 and then balance that versus the cost. So this is one of the considerations that each designer needs to make. In the CLT-EAT, these values here are modeled. We didn't have the measured data, but just to give an idea of what the impact is. We do find at least a plug here for the Rogers microwave calculator, MMWave, found on the website. We found that there's pretty good agreement between what we tend to model once one has the proper parameters for roughness on the copper to what we're actually measuring. So if you want to do some simulations easily, that you can do that online or download the program. Talking a little bit now into the area of PCB manufacturing considerations. So this is an area that's quite important. I know from my experience, an area that typically we don't get covered much in academia. We learn that on the job training, but very, very important because the success of a design, it also comes down to, is this something that is reproducible in manufacturing in high yield and as low in cost. So we mean that for these kinds of technology, we're starting to see more and more of the need that what we've seen in the past, and typically more in the military markets where maybe cost hadn't been as much a consideration, but in the commercial market space, cost is very, very important. The need for materials and sets that can be combined to make multi-layers, hybrid multi-layers with other materials like FR4, again, to keep costs down, where we're going to be mixing RF signals very, very high in frequency with maybe digital or much lower frequency analog signals. So some of the things that are important to always consider when you're looking into these rather complex multi-layers and that you may have maybe 5, 6, 10 layers, signal layers throughout in the constructions. You may have some vias that will be buried within the multi-layer. You'll have through vias, vias which typically go from the outside into tapping into an inner layer. So these are the things that are being now done more and more in these kinds of applications. So a couple of things to always remember when selecting that. A lot of times the coefficient of thermal expansion is a mechanical property that is very, very important to consider here in matching all these layers together to keep something, to manufacture something that is flat. Because usually then these will go through some process where you need to put devices on the surface. It's usually an automated system, and flatness of boards is a very, very important factor. So materials that have similar coefficient of thermal expansion in the X and the Y is important. As we said, it minimizes the bow and twist. It allows for the construction of materials that may be not just only of the material that you've selected for the RF, but also very important to have materials that have close match to that FR4 for the hybrid construction. So many materials in the traditional circuit board world are designed to be around 16, which is the value for copper, the copper foil that is used. So all the materials that are used in RF have that in mind. Some materials have significantly higher expansion coefficient, which can create a bow and twist situation. So that's one thing to look at in the data sheet and to take that into consideration. The other important factor, because many of them will have plated through holes, and reliability is going to be very important because they may be in environments where there's significant temperature variation. So the Z-axis expansion, pick materials with high Z-axis expansion, and a low Z-axis expansion and a high T sub G is important because this will allow the via to expand and contract, similar to what we tend to see in traditional FR4 materials. So when we say a low value is typically 80 parts per million per degree C or lower, tend to be materials that tend to have a high reliability. 50, better, 40, 30. So the lower the value, it'll be the highest reliability. We find that materials, when we do hybrid constructions of RF materials with FR4 materials, we find that usually the fault lines of breakpoints when we're doing extreme thermal cycling typically happens more in the FR4 than with materials that have which is around 80, 90 parts per million, versus materials that are around 40 to 50 in the Z-axis value. The other area that's important is that the selection of a bond ply, basically the bond layer that will adhere to various layers here. In case of RF materials, there's not that many that have let's say, temperature settings, lamination similar to that of the traditional FR4. So that's usually around 175 degrees Celsius for FR4. So, finding materials that have a low temperature, and, Rogers have designed the prepregs to be at 175, then you can then really combine various of these prepregs in a single multi-layer process. That is important because it helps then reduce the amount of lamination steps and helps reduce costs down. So a lamination temperature is important when selecting the bump plies for these materials on that. And then, of course, then you have to look at the impact of those layers in the sense of electrical performance, whether that is going to be the right how much is going to offset off of the core. So you may find that a material that you want to use has a dielectric constant of 2.1 versus a material that has 3.5. So now that has to be taken into account to the overall change in the composite of the dielectric constant. as well. And that I would say that it's important to remember here is not only regarding the copper foil, but then is the plating of selection. We have found in the past that when you're doing a plating process on the microstrip circuit, you will always have, and the way traditional circuits are made, you have that plating basically go on the surface on sides as well. This is the traditional electroless process in many chemistries versus the electrolytic. Electrolytic typically is done on the very top surface before the copper is etched. This is used as this layer is then used as the etch as a copper resist when you're etching. But this is traditional. And what here is that the current that travels on the circuit really travels mainly on the edges, and you have a lot of the current traveling on that plating. So when you see here the difference of some of these finishes, we can see that what happens is when you take rolled copper and you put rolled copper with electroless nickel immersion gold, which is the most common finish in the market for plating, for protection of the copper from oxidation. You have traditional ED copper here, and then once you put the plating, you see the impact on that. So you can see that the benefits, depending on the frequency band, the benefits of using a smooth copper can almost be negated by the plating finish that one may choose on there. So that is something that is sometimes obvious to designer as one's going through and selecting that area. So many choices that a designer has to make in order to achieve the best performing circuit. Here you'll see is looking at what happens to the current density in a microstrip circuit. Using, in this case, is a model modeled by the use of Sonnet software. Here we have a 20 mil material in the case of 4835 with a 50 ohm trace. So the current density is highest on the edges. It's 8 times greater than what you will find in the center. So that is what we mean when you put that plating on the edges of the trace where the current is going, and we know that the conductivity other than copper, silver is the only other metal that has a better conductivity. Anything that you will put on there will work against you in the sense of loss. Now, in the next slide here, we show some of the materials that have maybe different options here. So the first grouping here, we're just basically looking at the bare copper. We're looking at immersion silver, which is something that is starting to gain more and more acceptance by designers, by manufacturing. Circuit board facilities, typically in the past, silver was avoided because there had been some issues with reliability in the past. In talking with various other suppliers of these kinds of chemistries, they tell us that those issues of silver migration, whiskers have been addressed, and that today silver is a lot better and much more reliable. We're seeing it more and more, people trying to adopt this, particularly when you're designing in the 70, 77 gigahertz frequency bands. Then you have what happens with immersion tin, which seems to, I think, more commonly we're finding immersion tin more so than the electroless nickel immersion gold, which is the gray line here. And then something here called INIPIG, which is immersion nickel and gold, but it's got phosphorus as well on there. And so you can see the differences that happen. So solder mask, we get asked what happens to circuits when you put on the surface solder mask, because some people will do solder mask over bare copper. So this is data that we gathered, but in reality, Roger's going to have to remeasure this value, because what happens here is that the dielectric constant that was used in this and making the circuit took into account how much the effective dielectric constant would change, because you now have a solder mask material on top of the copper, and therefore it changes your effective dielectric constant, because it's no longer just air on top of that circuit. So this basically was a 50 ohm trace, taking into consideration that impact. So in reality, we should Rogers will remeasure this data to take into account that we'll take a traditional trace with 50 ohms here, apply solder mask, and probably you will see somewhat of a change, mainly because it changes the dielectric constant, but it probably won't be as much as what we hear, because this trace was really more narrow 50 ohm trace than it would have been here. And that's what kind of convoluting the problem here. So I would say, and summarizing here a little bit what we've covered. So from selecting the materials, as we said, depending on the frequency bands, depending on what one is trying to achieve, we can say that from a material perspective, the dielectric, copper, plating, you see many of these different areas are important to take into account, to be able to sit down with some of the material experts and then say, all right, this is what I'm trying to achieve. Can you give me some guidance into the direction? Many people typically will just say, give me the lowest loss dielectric, the lowest loss tangent, and I'm just going to go with that. But in some cases, that may be a good choice. But in some other cases, we're finding that the materials with the more balance of mid-dielectric constant around 3.0 seem to have a better overall balance of electrical mechanical stability, reliability concerns, and also have good enough losses, particularly when making proper selection of foil and plating. So it is something that one has to take into account, and the medium frequency bands, 27 gigahertz. Thermoset still quite widely used a lot today, and for these applications, we believe that will be the case as well. So the overall approach here is to take loss into consideration, but overall reliability is also a very, very important factor, and various of these materials may behave different depending on the environment. If it's a very high humidity environment, a very high temperature or low temperature environments, these things have to be taken into account as well. So that concludes at least the presentation portion if we have any questions, I believe you can type them in the chat area, and we'll be able to those over the next 12, 13 minutes that we have available in the hour.
Art, that's a very detailed and informative presentation. There are a lot of things to consider when you make materials choices. Art mentioned before we actually start the Q&A portion, I'll remind everyone that if you have registered for the webinar, which presumably you have because you're watching it, you'll shortly receive an email that has a link, and you can download Art's slides. If you have a question, just type it into the Q&A panel on the right-hand side of the WebEx screen, and we'll see how many questions we can answer in the next few minutes. Question, you talked some about this, but one of our viewers would like to have additional insight into the impact of the dielectric constant and thickness variation.
Oh, thank you, Gabriel. Yeah, very, very good question here, because electrical engineers, as I am, we tend to try to resolve everything by getting better dielectric constant. But when one looks at the equations of impedance and the variables of dielectric constant and thickness, one sees that the thickness is a directly proportional and effect to impedance, while dielectric constant is a square root effect. So one needs to look at the tolerances. Usually dielectric constant values, the tolerances are plus or minus 1, 1.5%, 2%. While thickness tolerances are typically 7.5 to 10%. So it looks at that and puts those values in the equation. A 50 ohm trace, you can find that if you take the extremes on thickness on a 50 ohm trace material, in the case that I was looking at 20 mil, this is the example that I remember off the top of my head, is that impact will cause a change of about 2 ohms for a 50 ohm trace. While you take the extreme of the dielectric constant values, that really only will affect about less than half an ohm. So if you're trying to approach a laminate supplier and say, hey, I need to have a more repeatable product in my design, and you're focused just on dielectric constant, you may not get, as we would say, as big a bang for your buck when you're trying to tighten the dielectric constant versus requesting we work on improving the thickness variation of this product so we can have a much more repeatable 50-ohm traces. So that's one of the things, as we said, is that look at those tolerances. They're much broader in thickness and a direct relationship to impedance versus the square roots versus the Dielectric constants, which are a square root effect on impedance. I hope that explains a little bit better that.
Okay, thank you. Another question, can you discuss how nickel gold plating behaves compared to what you showed in the examples?
Okay, so in this particular example here, so hopefully you'll be able to see that here. I'm going back to the slide on surface finish effects on insertion loss that had the graphic of the cut cross sections of the traces. So electroless nickel immersion gold is what you would have in this case here, where basically the plating happens after your circuit traces have been etched. So the plating, this layer that is electroless nickel applied over the copper, so that's this gray surface here, and then immersion gold is applied afterward, which is a very thin layer of gold that then covers the surface. So what you'll see here is that when you have the copper in this versus the effect of the electroless nickel ENIG, what says ENIG, electroless nickel immersion gold, you can see the impact on this particular circuit. In this case, it's 5 mil RO 3003, so a DK3 material with loss tangent of 0.001. You can see the impact that you will have once you add that to it. When people do, and typically we see more in the defense industry, the electrolytic process. And again, what happens is that before any copper gets etched, they will plate on the surface just the pattern of the circuit, and the circuit goes and gets etched. That's why you don't get copper plating. The nickel or gold plating on the edges here. So your current running through here is not affected. But as I said, typically this is something we find more for the defense markets, because they're going to be then doing some wire bonding. So they have to have what they call hard gold on the surface, and this is the way they do it. But it's a much more costly process. For circuits, this is the traditional way, and it will have that impact. We have separate presentations that they can reach out if they need more detail on subject that Rogers has presented, but that is something to consider. So here's the start here where you will see the data on ENIC, which is electroless nickel immersion gold.
For LCP material, how is the stability with the temperature and the shrinkage in thickness when it's laminated?
The LCP material, the one thing to take into consideration is that it's an unsupported material, so it's not so much the shrinkage, but it's because of the extreme flexibility of this product. So we found that the facilities that process LCP, if these are facilities that have experience in working with flex circuit materials, polyimide materials, for example, they tend to be able to have better approach on how to manage this so that they don't stretch materials in the handling, because they're used to doing that. The circuit board facilities that tend to process more rigid, it may be something that they have to learn to adapt, but it's not something that can't be done. Rogers does have technical experts that will work with facilities that once somebody understands that these materials do have a difference in how they behave, and we've seen this as well with very thin of the RO 3000 materials, thin. Same thing is that how you handle it in the process, you can particularly stretch it and then it doesn't behave in a consistent manner. That once these things are understood and then adopted in how to manage it, that you can make successful builds. But it's something that does require early discussion on how to go about and design and process it versus just throwing in and treat it as a normal layer of Thermoset or a thicker PTFE. So that indeed, I would say it's a lot more specific application to application what it's trying to achieve. I would say the main limitation we found in LCP has been mainly in that if somebody's trying to do a complex multilayer with buried vias, so sequential lamination cannot be done with the traditional LCP bond ply, so it requires using other kinds of bond plies or prepregs to be able to do sequential lamination on an LCP material.
For millimeter wave applications, would conductance loss or dielectric loss be the more dominant factor? And can you cite an example?
I don't have the data here in front of me, but typically and again, you can go to the MMWave 17 calculator and download it on the internet from the Rogers website. But when you sit down and you look at what happens on the conductor and dielectric losses, what happens is as you go thinner and thinner in the dielectric, or your 50 ohm trace, and assuming it's a 50 ohm trace, your trace becomes narrower. So as you go thinner in dielectric, you will see bigger impact to the conductor loss. So at high enough frequencies, you do find that the conductor losses are a very, very significant portion. So that is what governs quite a bit, assuming that you do have a low loss system. If you don't have a low loss resin, and then it's a different story. Then you can't have as much an impact on dielectric losses as you do on conductor losses. But for these materials that I've listed in this table, if you go to high enough frequencies, you will find that mainly for loss tangent materials at frequencies and thin dielectrics, which would be the case for high frequencies, conductor losses could be 75–80% of your overall insertion loss over the dielectric.
Okay, one of our viewers is working on an application that's a multi-layer miniaturized antenna and would like to know whether it makes sense to use bond ply for high dielectric constant substrates, for example, in the range of 10.2.
Okay. Well, it depends also the frequency band that you would be operating in. So we find that, yes, high dielectric constant materials do have an advantage in reducing the size, obviously, of the circuit. Wavelength, there are smaller circuit features. On the frequency band that you're at, maybe the losses, because usually the conductor losses, being narrow traces, will increase. So it's an advantage. We have seen some folks using high dielectric constant materials, trying to do higher dielectric constant prepregs. That currently your options on high dielectric constant prepregs limited. We know of people who use some of the PTFE materials lamination, so the raw PTFE ceramic of dielectric constant 10, to use that as a bond ply, but that requires to take the multilayer to a very high temperature lamination. In essence, you are remelting the Teflon and using that as your bond ply in what's called fusion bonding. So not many facilities have the ability to go to the required temperatures of 325 Celsius, but some people can, and some people have done that. So it is something that is possible. I would say probably we might want to contact one of the technical people within Rogers to go over more specifics to that, but it is possible. I would just probably, in understanding better the frequency band and overall capability of the circuit board facilities that you're working with is whether this would be the best option or not.
Yeah, makes sense. Our last question that we'll have time for, does Rogers have guidelines for unbalanced construction so that you can fabricate the boards to reduce warpage?
I would say yes. There's in the sense that we have knowledge as to what we find would be an issue or not. I don't believe we have it per se in a written form on our website, but contacting what are our technical service engineers, our TSEs, they have a lot of experience in working in this area. So all constructions that we have found out there are balanced. Sometimes we find that you have an FR4 multilayer and then you have an RF cap layer on just one side. And again, taking into account the CTE values of the materials, and you find that those can be built without concern that the board come out warped. Not always do you need to then have an RF material on both ends to balance it. So we do have experience in that, and that can be shared. But we do find that there's enough individual variation that can happen that we'd rather sit down and talk about whether a particular construction thickness of the dielectric, thickness of the FR4, or the different layers, that may be a difference as well. So it's always difficult to just have a general the rules. But we do have experience in that, and it can be done, which is typically not recommended in just traditional FR4 multi-layers.
Unfortunately, we've run out of time for more questions. I think we were able to get through most of them, but apologies to those of you whose questions were not answered. Rogers will get copies of all these questions that you asked, so they can follow up with you. I'd like to thank Art Aguayo of Rogers for the detailed and interesting presentation, and to Rogers for obviously sponsoring the webinar. This has been recorded, and it will be available for replay from the events section of the Microwave Journal website within about 24 hours. So if you'd like to watch it again, or if your colleagues would benefit from watching it, please let them know. So everyone who registered will receive an email within the next 30 minutes that will have a link so you can download today's slides. Thanks everyone for joining us today.
Thank you.